Okay, we want to look at quadratic functions, and we're in pretty good shape to do that because everybody's pretty good with the quadratic formula and transformations of graphs. I'm going to do something tiny down here because I want to show you what this whole messy diagram here is all about. So we start here with our basic x squared function, because any quadratic function of the form f of x equals ax squared plus bx plus c has a parabolic graph. And that parabolic graph is a transformed, complete basic squaring function. You can't really read the word complete. I was seeing complex. Kind of looks that way. But yeah, I just wrote that a couple of hours ago. Transformed, complete, basic squaring function. It's of the form y equals f of x equals big A x minus h quantity squared plus k. And if we expand the x minus h, we get an x squared there. It's the only x squared in the equation. So that we have capital A times x squared. But of course our function is little a times x squared, so in this case capital A is the same as little a. So the form is little a times x minus h squared plus k, where little a equals this. Now we have to determine h and k, but we've got little a. And we can determine h and k, which are the horizontal and vertical shifts, from the we can determine h from the quadratic formula and use that result to find k. Okay, so let's look at the transformations that get us from here to here. So we have a y equals x squared function. I'm not specifying what the function is. I just sketched a graph. So right here we've vertically stretched the graph. After vertically stretching it, we shift it over here. It's supposed to have the same shape, a little hard to draw down here. Okay, then we vertically shift it downward. And now we put a scale on the graph, which I've got here. So this graph is the same as this one. You see the original graph, you see the purple graph, you see the yellow graph here, vertex down here, and you see the orange graph with its vertex down here. Okay, now I just drew that. I drew that and I put a scale on it. The scale fits the basic function, -2 to 2, 0 to 4. So there's our basic quadratic function. Now we want to determine what the equation of this orange graph is. After the x squared function is stretched, shifted to the right, and shifted down, what is the equation of that function? So by making estimates, we learn a lot about the properties of the graph, and we get a bigger perspective on quadratic functions, which is our next big topic. Okay, well, making estimates. Okay, ask you to estimate the x-intercepts, the axis of symmetry, in the zeros of f of x. Okay, well, the x-intercepts. First of all, what are the x-intercepts? Because some people had a little trouble answering this. The x-intercepts are the points where the graph we're after, which is the orange graph, goes through the x-axis. That's what an x-intercept is. So by putting a scale on this, first of all, people estimated that our horizontal shift was about 4 units. So we went from here to here. This yellow arrow here shows us that we shifted this purple graph over 4 units to get the yellow graph. and then estimated that we shifted down 4 units to get the orange graph. Okay, those are very reasonable estimates. So that tells us that we have 4 on the x-axis. You can almost see it, but it's been kind of written over. So 4 on the x-axis, well, there's 2, so there's 4. That makes sense. And then 4 units in the y direction. It looks like that's about what we did. So we have a horizontal shift of 4, vertical shift of -4. Now we know what h and k are. Okay, well, now we're going to proceed to try to figure out a. Now we can estimate a. So actually we did that. Okay, we estimate a to get our vertical stretch factor. Okay, our vertical stretch factor is a. So by how much is this purple graph vertically stretched from the white graph? Well, we can make an estimate of that stretch. We could take any point x. We took a point here, some point x, and drew a white arrow up to the graph of the x squared function. And that represents the y value for this x. And then we drew a purple arrow up to the graph of the purple function. And we saw that, well, that arrow is about 1, 2, 3, maybe 3.5 times as long as this arrow, meaning that the y-coordinate here is 3.5 times as great as it is here, meaning that the x squared function was vertically stretched by a factor of 3.5. Now, we came over here just to check and see if that stretch factor worked, and we found that our purple arrow was only about twice as long as our white arrow. And then we checked here and saw the purple arrow was a little more than twice as much. So over here it looks like it's 4 times as much. Over here it looks like it's 2.5 times as much. Well, that's because this is a hand sketch, and drawing a skinny parabola is kind of difficult. And, you know, I'm no expert at this, so they're at drawing the thing, so there we have it. We're not sure if our vertical stretch factor is 4 or 2 or 2.5, so we settled on 3. Okay, vertical stretch factor is 3. So that's an estimate. Okay, so that's fine. Now let's make a couple more estimates. And we're going to see if those estimates are consistent with the estimates we made for the horizontal shift of 4, vertical shift of -4, and the vertical stretch factor of 3. So, what are x-intercepts? People had trouble. Most people couldn't answer this. The x-intercept is the point where the graph intersects the x-axis. So here's our graph, the orange graph. Let's accent it a little bit. Okay, it goes through the x-axis here and here. Estimate those points. Here's 2, here's 4. What's this? What's this? Well, this looks like it's halfway between 2 and 4, so 3 is a pretty good estimate, pretty straightforward estimate. Well, the quadratic formula ensures, okay, never mind. Computer just went off. I should have just shut the lid because it's not doing anything. Okay. We've had a lot of glitches this morning, so I thought we had enough. And my immediate response is, oh, something happened. Apparently the monitor just decided it wanted to turn off. Okay, so back to here. We estimate one of the intercepts is at 3, 0, halfway between 2 and 4. It's obvious. From the quadratic formula, the intercepts occur at equal distances on both sides of the axis of symmetry. Now we'll see that more specifically later, but that's one of your basic properties. So if this is 3 and this is 4, this has to be 5. And it looks about right. It looks like it's a little closer to 4 than this is, but that's just because I didn't draw a perfect graph. So the intercept is 5, 0. So there are our intercepts. What's the axis of symmetry? Well, For the x squared function, the white function here, the axis of symmetry is the y-axis. It's reflection from one side to the other. Okay, that's your basic symmetry that we know about. That is inherited by the fact that we vertically stretch this factor by a uniform, we vertically stretch this graph by a uniform factor to get the purple graph. Axis of symmetry is still the y-axis. If we shift 4 units to the right, the axis of symmetry becomes the line x equals 4. Okay, it goes from x equals 0, which is your y-axis, to x equals 4. So there's your axis of symmetry. Where are the zeros of the function? Well, people didn't seem to understand that terminology. Now, I've used it, but I'm not sure we really defined it, so maybe everybody has an excuse. The zeros of the function are the values of x where the function takes value 0. F of x equals 0 at the 0 of the function. So the zeros are the points where f of x equals 0. Where does f of x equal 0? Well, f of x is your y-coordinate. Your y-coordinate then has to be 0. Where is the y-coordinate? On the x-axis. So your zeros are the points, the values of x on the x-axis where the graph cuts through that axis. So the zeros are at x equals 3 and x equals 5. Now the difference between the intercepts and zeros, the intercepts are points and they have 2 coordinates. Zeros are just the values of x at those 2 coordinates though. Okay, so from everything that we've done, remember that the form is a times x minus h squared plus k. We've estimated that the vertical stretch is a, which is 3, so that means a is going to be 3. H is 4, it's x minus h, so it's x minus 4. And k is negative 4, so we have a negative 4 here. We can expand this square. We get x squared minus 8x plus 16. We can multiply that by 3 and subtract 4, and you can verify that this is what we get. Now, what does the quadratic formula tell us about a graph? It tells us that x equals 0 if and only if x equals negative a plus or minus a, yada, yada, yada. Okay, well, a is 3, b is negative 24, c is 44. I don't think I've ever used yada, yada, yada. I didn't used to watch Seinfeld, I think that's where it came from. Okay, again, a is 3, b is negative 24, c is 44. We plug that into the quadratic formula, there it is. Then we do the arithmetic, and here it is. Okay, now, 24 over 6 plus or minus square root of 48 over 6. Okay, square root of 48 is about 6.9. 24 over 6 is 4. 6.9 divided by 6 is 1.15. So we have 4 plus or minus 1.15 telling us that if this is, in fact, the equation of that thing that I drew, the x-intercept ought to be 5.15, 4 plus 1.15, or 2.85, which is 4 minus 1.15. Now, you all helped me, the class helped me with the estimates. I used estimates from the class and modified one of them a little bit, but just the vertical stretch. Somebody estimated 2, which is kind of consistent with some of these points, not the others, so I went up to 3. But I used the 4 and the negative 4, and it all came out this way. It tells us that the zeros of this function are at 5.15 and 2.85. Now, compare that with the estimated 3 and 5. Well, 5.15 is just a little more than 5. 2.85 is just a little less than 3. I give us a star. I think that's pretty good consistency. By estimating these things and estimating somewhat carefully, we came up with an equation. We applied the quadratic formula to the equation, the properties, and we've got all this. Now the only thing we haven't verified, because we've come pretty close to verifying the zeros, we haven't verified that the y-coordinate of this vertex should be negative 4. if the equation predicts a y-coordinate of a vertex at -4, then that's a pretty good indication that everything works and everything is nice and consistent, and we have a good understanding of quadratic functions. Well, let's see, now I did that somewhere, and if I can't pull that out kind of quickly, okay, we have to do that in another video. I can't locate that board real quickly. I think I know where it is, but